Okay, now let's take a look at what an object-oriented queue implementation is going to look like. So queues are a little bit more complicated than stacks. If you haven't watched the stack pseudocode video yet, I highly recommend it to get a sense for what that implementation looks like. With a queue though, we might start at the beginning and start growing over here. But what happens is eventually you may end up with a queue, where you've got data here, and it may eventually grow all the way to the end, and you want to add one more new thing. Well, guess what? You've got space, but it's over here. So queue array implementations require a little bit more particular it does require a little more calculations and figuring out where do we put the next element. So inserts become slightly more challenging. Linked lists is fairly easy because everything's a pointer. So let's take a look at what we need to set up for an array. So with a queue, unlike a stack just starts at the beginning. So I can just use 0 as the baseline. But for a queue, I actually want to keep track of two things. I want to keep track of the front of the queue and the tail of the queue. And so I had a top with the stack array implementation, which I initialized to -1. And so I'm going to do the same thing here, but now I'm going to keep track of my front and my tail. And so when I insert, so let's see, we've got, so if I'm reading something, we're going to read from the top. This is like our peek function. So we're just going to return, actually, if it's -1, we don't want to do that. So if front does not equal -1, we're going to return our array front. Otherwise, we'll just return null if it's empty. Okay, so that's what's going to happen if our queue is empty. We could also replace this with an isEmpty function, like we did with stack, but I'm not going to take the time to do that here because we've already done that once. So insert has a little bit, and hopefully I can fit it here. It's got, maybe I'll make this bigger so my writing will be smaller. Okay, so what we have with insert is we're going to create our new node of our item, and then we need to test to see if it's empty. So we could do an isEmpty function. I'm going to say if tail plus 1 equals the front, we're just going to print an error. Okay, so this is our is full check. So you can make a function for this as well. Okay, and you may need to look around and see, you might need some modulus on that tail. We'll get into that in a little bit later. So now what we want to check to see is if the front is less than 0 and the tail is less than 0. So this is an isEmpty check. So if it's full, we're just going to print out an error because this is a fixed sized queue implementation. So if it's full, then we just don't do anything because it's a fixed sized queue. If it's empty, then we are going to point the front and the tail to the same thing. Front is going to equal 0 and tail is going to equal 0. And then otherwise, if it's not empty, so this is the otherwise case, so otherwise, we are simply going to say, not so simple, tail equals tail plus 1 modulus the length of the array. Okay, what am I doing here? So what this is saying is that I'm going to move my tail pointer over. But imagine for a second that my tail is here, right? Let's say this is your front and this is your tail. If I add plus 1, It's going to be out of bounds. And the way what I really want it to have happen is tail plus 1 should really point back to 0. The way I do that is with modulus. Remember, we've had modulus, so modulus evenly divides and it keeps the remainder. So if we do tail plus 1 modulus the length, it's going to move my tail back into the 0 to 1 less than the length range. It's going to do that for me. So that's why we have it here. And then finally, once we've figured out where the tail is, I'm going to set my array tail equal to my new node. So insert has a little bit more cases, a little bit more calculations to get this working for Q. We didn't have to deal with this for a stack because the stack just became full once it reached the end. And so we didn't have to like wind around our Q. But here we might have blank spaces in the beginning. And so, we need to access those. Okay. And so now we're going to be looking at remove. So if our front equals -1, so this is the is empty check. So if you implemented is full or is empty functions, that's great. You can use those here. I'm not for this one. We're going to return null. Then we're going to have a new node T. So we're going to have a temp var equal to array front. And then our front update is going to be the same as our tail update before. We're going to modulus the length of the array. So we only had to figure out how to do this trick once. This was our approach. This is how we can clamp our index values for front and tail onto 0 to length of array. And so the way we do that is by using modulus. And so once we figured out the trick to do that, or our solution for that, we can keep using it. And then I'm going to return our temporary item. Oh, array front. There we go. Need some square braces there. Awesome. And so search is going to be very, very similar to what it was before. We do want to be a little bit careful that we're going from the front to the tail. So I'm going to actually elect to do a loop here. So for I equal to front, I mod length of array less than tail, I plus plus. If item, if our item equals array, I'm not modifying this, I'm just making sure the I is always in the right spot. So if the item is the same as the array, I mod the length. You could also put the I mod the length calculation here at the beginning. And then you wouldn't need it in your for loop if you're always checking it. But you have to either check it or change it. If we find it, we return true. Otherwise, we simply, return false, but I need to move this over a little bit. Okay. If we don't find it in this for loop, then we return false. Okay. Awesome, awesome. Let's take a look at actually, before we take a look at linked lists, let's see how resizable changes. And remember, resizable, I'm just going to delete this because really what happens is that this is the same. The only thing that changes is our insert, and that really stays the same, except for if it's full. So So same, except on the is full check. So in the is full check, we're going to increase the size. Array new equals an array of length of array times 2, and I'm just going over into the linked list portion because that's also going to be the same. For I in, well, actually we can't really do for, we could do for I in range, length of the array. So we need to copy everything over. So array, new array, new I equals array I. So we're gonna copy values that we might not need to copy. You can make this more efficient by going from front to tail, as I did in the search loop up here. We could be slightly more efficient, but the idea is we have to copy everything over, and then we say array equals array new. Okay, and so this is just this little piece goes in where here, where we had the is full check. Okay, so I'll put a little star here so we know that's the only difference. Okay, awesome. So let's take a look at linked list. Linked list is really nice for implementing stacks and queues, I have to say. Once you start dealing with arrays and you see all the, all the machinations that you have to go through, linked lists become a lot simpler. So for implementing a queue, I want to add a couple things. First off is I want to add a previous. This is going to be a doubly linked list. I also want a tail pointer. This is so that we can ensure that our operations are as optimal as possible in the worst case, so that our big O's are O of 1 instead of O of n all the time. Okay, so reading is pretty simple. Now you do have to pick, I'm going to assume the head is the beginning and the tail is the end. So we want to return the beginning of the list, so I'm going to return the head. For insert, I'm going to create a new node. I can't remember if I did this for stacks. If I didn't, you don't have to take this extra step. It's kind of flexible in pseudocode, but at some point you would need a node. If it's empty, so if the head is null, we're following the same path, we would say the head equals n and the tail equals n. So this is our is empty. Check here. It's our is empty case. Otherwise, I need a little more space here. N.next is going to equal head. So no, I'm adding to the tail and returning the head. Oops, but you can do it either way. So the original implementation I'm following along with did it a different way. So we can say I'm going to add to the tail. So tail dot next equals n, and then tail equals n. You can do it either way, right? You can pull from the tail. These things work together. So what I could say is an alternative might be return tail if this is the end and this is the beginning. And then here I would say something like head.next equals n and head equals n, right? So these are two alternatives. Actually, I'm going to erase this and just say alternative. Okay, that's just to make sure that we kind of cover all the cases. So again, this is an alternative. You wouldn't do both of these things. Let's start with the first way where we're pulling from the beginning and adding to the end. So with remove, I'm returning from the beginning, and I'm going to also add to the beginning. So in that case, what I'm going to say is I'm going to create a temp. I'm going to set that equal to the head. I'm going to return that. I'm going to say head equals head.next. And then I'm just going to simply not quite sure what happened there. And then I'm going to return the head. The alternative I'm going to use is to say temp equals tail. Tail equals tail dot previous. I have one more step here. I have to set the tail dot next equal to null. And then I'm going to return temp. Okay, so we have two different implementations, but the thing is you want them to work in concert together. So we can either assume the head is the beginning, and that's where we're peeking from with read. That's where we're removing from. Like these things work together. And then insert is different. Insert would be working with the tail. But if we assume an alternative, it doesn't matter to me. You can call head, tail, you can call them whatever you want. You can NQ or DQ at either end, but you just have to be consistent. And so if you do change that, then you would want to, you'd have to switch it around when you're reading and removing. Okay, pardon me. All right. So let's take a look at search. I'm just going to do a quick check because I'm pretty sure the search is the same. So we would go through all the items. Yep, it's going to be the same as stack. So this is going to, we're going to save us a little time. A little bit. So we're going to save this ourselves a little bit of time and say this is same as stack linked list. Awesome, and there you have it. And remember, for linked lists, there is no difference between fixed and resizable because linked lists are always resizable.